Okay, today we're going to be talking about Chapter 9, Modeling Our World, which is going to get into linear modeling. And basically all linear modeling means is that when you plot all the points in your data, they come really, really close to making a straight line, and you can use that to make predictions about what is about to happen. So the first example that we have says, imagine that we measure the depth of rain accumulated in a range gauge as a steady rainfall. So we've just gone outside, we have a rain, it's filling up with rain. We kind of look at it for 6 hours and we record what the depth is in inches. So in the first hour we look and there's about 1 inch there. Okay, in the second hour we look and there's about 2 inches there. In the third hour we look and there's about 3 inches there, and so on and so forth. So this is a graph of that function. The slope of the line is the amount it rises divided by the amount it rains. So when you look at your slope, if you compare this point to this point, well, we would go over 1 hour and up 1 inch. And usually when we talk about slope, we talk about rise over run. Okay, so I like to kind of go the opposite way and go up and over. So we would go up. Well, what are the units when we go up? We're talking about inches. So we would go up 1 inch and then go over, which is the run part, every 1 hour, which is how they're coming up with this 1 inch over 1 hour, which is our rate and also our slope, which are very similar. In fact, they're the same thing. Sometimes we talk about them in a little bit different manner, but slope and rate go together. So basically, our slope is 1 inch every hour, and that's also our rate. Remember, in the last section, we talked about the independent variable is always your x, the dependent variable is always your y. And if you have a graph already there for you, it's easy to tell what your independent variable and your dependent variable is because this is your x-axis and this is your y-axis. So if you have the information that the independent variable is the x, well, what is that? On the x-axis, we have time in hours, and on the y-axis, we have rain depth in feet. Okay, and we talked about how our dependent variable depends on our independent variable. Well, if no more time passes, then the rain is not going to get any deeper. So our dependent variable always depends on our independent variable. The rain depth increased 1 inch an hour. The rate of change of the rain depth with respect to time was 1 inch per hour, or 1 inch for every hour. Just different ways to write that. A linear function is a function that has a constant rate of change, and when you graph it, it makes a straight line. So we've got some examples of finding slope down here. And it says, what is the slope of the line? And we talked about how it's rise over run. Okay, so they draw it underneath. I like to draw it on the top. So you go up 0.5 or half of an inch for every, when you go over to meet the line, 1 hour. Okay, so when we reduce this, 0.5 divided by 1 is just 0.5 inches per hour. And usually when we talk about slope, we don't put the units down, we just put the number. So our slope is 0.5 or 1/2. Our rate of change is actually 1/2 an inch every hour. Okay, same thing here. If we looked at this one, we're actually, if you look at the rise part, you're going up from 3 to 4.5. On this little section would be 3 to 4.5 if you went back and looked at where you're drawing your line. So that would be going up 1.5. So that's where they're getting this 1.5 on the top. Can't even see that, sorry, let me. So our rise would be 1.5, and that's in inches. And our run would be how much do we go over, and it's 1 hour. So every 1 hour. Okay, they've divided 1.5 divided by 1, and they got 1.5 inches per hour. So the slope of the line is 1.5. The rate of change is 1.5 inches per hour. Okay, on this one, we would want to do rise over run. So it looks to me like we're going up to get from one point to the next, we would go up 2 inches, and then we would go over 1 hour. Okay, and 2 divided by 1 would just give you your 2 inches per hour. So that's your slope. Rate of change, you would add the units of 2 inches per hour. Okay. The amount that the graph of a function rises vertically for a given distance that it runs horizontally is your slope. That's why, so this is your rise over your run. The rise is vertical. The run is horizontal. So the amount that a graph rises vertically given distance that it runs horizontally, just another way to word that. We talked about how it's rise over run. The slope is equal to the rate of change. So they're the same thing. A lot of times when we talk about rate of change, we're adding on the units. A linear function has a constant rate of change and a straight line graph. The rate of change is equal to the slope of the graph. The greater the rate of change, the steeper the slope. Kind of like if you were looking at a mountain. Okay, the steeper the mountain, that would be the greater rate of change. You calculate the rate of change by finding the slope between any 2 points on a graph. So another way to think about the slope is the change in the dependent variable, which is your rise, over the change of your independent variable, which is your run that we talked about before. So here we have example 1. It says you hike a 3-mile trail starting at an elevation of 8,000 feet. So here we are at the very beginning, our starting point, and we're starting out at 8,000 feet. Our distance in miles, none has gone by. We're beginning at 8,000 feet of elevation. Along the way, the trail gains elevation at a constant rate of 650 feet per mile. So what does that mean? Every time we go 1 mile, we're going to go up 650 feet. The elevation along the trail in feet can be viewed as a function of distance walked in miles. What is the domain of the function? That gives your elevation as you hike, along. Does this model seem realistic? Okay. Well, domain is a fancy word for saying your x value. Okay. And our domain here, we can tell because we've got a graph, is also our independent variable. And it is distance in miles. Okay, does this model seem realistic? Well, yeah, I mean, that's is it possible that if you hike a mile, you're going to go up 650 feet? I think so. There's 5,280 feet in a mile. So it would be realistic that we would be able to climb in altitude 650 feet every mile. So yes, yes, it's realistic. Okay. The only thing that I would add to that is that, if you're hiking up if you've ever been to like Pinnacle Mountain to hike or something else like that, there's parts of it that are steeper and parts of it that are more flat. And so I guess it's partially unrealistic just because there are different elevations. There's different times whenever the mountain is getting steeper faster and not as steep in some places. So we need to consider that. So it probably, if you graphed it, it probably wouldn't make a perfectly straight line, but it is realistic to think you could go up 650 feet per mile. Okay, let's look at example 2. A small store sells fresh pineapples. Based on data for pineapple prices between $2 and $5, the store owner created a model in which a linear function is used to describe how the demand or the number of pineapples sold per day varies with the price. Okay, so for example, the point 280, if we go to our graph and look at the point where the pineapples are $2 and the demand of pineapples is 80, it's this point right here, $2.80 pineapples. Means that at the price of $2 per pineapple, 80 pineapples can be sold on average on an average day. So what is the rate of change for this function? Discuss the validity of this model. So we also have another point that they plotted here that says if they sell 5 pineapples, then they're only gonna, and they've got the point written down right here, or I wouldn't know because it's really close. It's under 60, but it doesn't look like it's exactly halfway in between, but 550. So if they sell their pineapples for $5, they're only going to be able to sell 50 of them, versus if they sell them for $2, they're going to be able to sell them for 80. So remember that we do rise over run. Okay, so it looks like to get from this point on the left to this point, and I always go from the point on the left to the point on the right. You wouldn't go up, you would go down. Okay, and the amount you would go down. So this is 80, and then this was 50 pineapples. So we would actually be, and this is where they've got 50 minus 80. We're going down, which is that top part would give us negative 30. And then the run part is where you go from here, this point to this point, and we're actually running to the right, so that's going to be positive. If you go down, you're going to be negative. If you're running to the right, that's going to be positive. And so it looks like we're running from 5 to 2, which is going to be a positive 3. We would go over 3 spaces. Okay, and if we divide that, that's negative 10. And what are we talking about here? Well, the negative 30 was the number of pineapples. And the 3 was talking about the price. So this means that this number right here means that we have negative 10 pineapples per dollar. And we probably want to add on the fact that it dollar of an increase. So every time we add and charge one more dollar, we're going to sell 10 less pineapples. Okay. So the rate of change rule allows us to calculate the change in the dependent variable from the change in the independent variable. So the change in the dependent variable, you're going to take your rate of change and multiply it by the change in the independent variable. It says, using the linear demand function in the figure below, predict the change in demand for pineapples if the price increases by $3. Okay, well, we already know that we found out in the previous example that we have negative 10 pineapples per dollar. And if we're going to raise the price by $3, then we would do negative 10 times 3, which would give us a loss of negative 30, or we're selling 30 less pineapples if we raise the price. Okay, that's a prediction I can make based on my slope. Suppose your job is to oversee an automated assembly line that manufactures computer chips. You arrive at work one day to find a stock of 25 chips that were produced during the night. If chips are produced at a constant rate of 4 chips per hour, how large is the stock of chips at any particular time during the shift? Find the linear function that describes how the number of chips depend on the time of day. So the goal is to write an equation for the function. First, let's describe the stock of chips at any particular time with a word equation. Okay, so we could say, well, the number of chips is equal to the initial number of chips. So how many we had in the beginning, and plus the change in the number of chips. Okay, so it's going to equal what we had in the beginning plus any change we had in number of chips. For the last term above, the change in the number of chips, so how do we figure out what the change in number of chips is? It looks like we're going to have, if you look at, they found the slope here, we go up 4 and over 1, so 4 chips per hour. So to calculate the change in the number of chips, we've got 4, it's going to change 4 chips every hour. So we're going to multiply that by the elapsed time, or how much time has gone by. Okay. So if we put the two equations together and using 25 for the initial number of chips, okay, because they told us in the problem, so we know that the initial number of chips, so I'm filling out this formula right here. The initial number of chips is 25, is what we would plug in for this, plus the change in chips, which is this part down here, 4 chips per hour times the elapsed time. We can make an equation that says, well, the number of chips is 25 plus 4 t. And t would stand for the number of hours that has gone by. So let's look up here. Did they tell us how many hours are going to go by? It says if chips are produced at a constant rate of 4 chips per hour, how large is the stock of chips at any particular time during your shift? Find the linear function that describes how the number of chips depends on the time of day. Okay, so if 3.5 hours have gone by, we would say, well, the number of chips is 25, and I'm just picking something to give you an example. So 25 plus 4 times 3.5, that's going to give us 39 chips. Okay. So if I wanted to see how many chips we would have after 9 hours went by, so if the time is 3.5 hours, we would get this. If the time is 9 hours, we would say, well, the number of chips is 25 plus 9 times, plus 4, because with 4 chips per hour, 4 times 9, I would plug in 9 for the t. Okay, and That should be quite a bit more. So 4 plus 4 times 9. I'm sorry, 25. I don't know what I'm doing today. Sorry. 25 plus 4 times 9 is 61 chips. Okay, so in this problem, the slope is the 4. This is our y-intercept. And we also call it our starting point. This is how many chips we started out with. The slope is always written in front of the number that you're going to multiply whatever it's changing by. And we're going to talk about that a little bit more in just a minute. But to generalize from this example to any linear function, the number of chips, n, is the dependent variable. The time t is the independent variable. The initial stock of 25 chips represents the initial value of the independent variable when the time is equal to 0. The term 4 chips per hour is the rate of change. Also, we call that the slope with respect to t. So chips per hour times t is the change in n. So if we want to write an equation, here's a general equation for a linear function. You're going to do the dependent variable is equal to the initial value, which is also called your y-intercept. And you're going to add that to your slope, which is your rate of change, times whatever your independent variable is. So it depends on what you want to call this. Sometimes we just have an x here. In algebra, x is commonly used for the independent variable and for the dependent variable. For a straight line, the slope is usually denoted by m, which is weird because you would think slope would be s, and the initial value, or the y-intercept, which is what I was talking about before, is called a b. So this, in this equation, m is your slope or your rate of change, b is your y-intercept, and a lot of times we call that our starting point, how much we had to begin with. This equation is important. Okay, so when we're looking at these lines right here, the equation, I'm going to write this big, it's written here, but y equals 4x minus 4 is the equation for this line. The number that is in front of the x is the slope, or your rate of change. And you can see here that they've calculated the slope. The rise over run was 4 over 1, so it was 4. This number that's not in front of the x is your starting point, or your y-intercept. So if you look on your graph, you're going to want to look at your y-axis. You're going to want to notice that it crosses the y-axis at -4, which is why they have, that's your starting point. When no time has gone by, when x is 0 right here, what is your y value? And it's -4. So that's how they came up with that. Okay. These three lines have different slopes, so you can see the different colors. They're all going different ways, but they have the same y-intercept. They have the same starting point, which is right here. These three lines all have the same slope, but the y-intercepts are all different. They cross the y-axis at a different place. These cross the y-axis at the same place. Okay. So it says use the function shown to the right to write an equation that describes the rain depth at any time after the storm began. Use the equation to find the rain depth 4 hours after the storm began. So we want to find the rain depth. So we could say the depth is equal to, right? Well, we're trying to model after this y equals mx plus b. So for our dependent variable, we just chose to use the letter D for that. X is automatically going to be there unless you want to call it something different. Some people would use T for time because this is in time. Doesn't matter. Okay, M is your slope. So it looks like they've already calculated our slope for us here, but you would go, our rise over run is, we're going up 1 hour over 1 inch. So if you reduce that, 1 divided by 1 is just 1 hour per inch. Okay, this is your y-intercept or your starting point. So you're going to go and you're going to look at your y-axis like we were doing before. We're going to go, okay, on my y-axis, where does the red line cross? And it looks like it starts right here at 0. So we would put plus 0. So if they want to know what the rain depth is after 4 hours, we would plug in a 4 for x. So we say, well, the depth is 1 times 4 plus 0, which is going to give us 4 inches. Okay, and we kind of want to check. If we go to 4, we go up, we go over, that's correct. 4 hours gives us 4 inches. Okay. Alcohol is metabolized by the body using enzymes in the liver in such a way that the blood alcohol content decreases linearly. A study by the National Institute on Alcohol Abuse and Alcoholism showed that for a group of fasting males who consumed 4 drinks rapidly, the blood alcohol content rose to a maximum of 0.08 grams per 100 milliliters, about an hour after the drinks were consumed. Okay, one thing I'm noticing here is this looks like a rate. And when you have a rate of change, that's probably going to be your slope. So after 4 drinks rapidly, the blood alcohol content rose to a maximum of 0.08 grams per 100 milliliters, about an hour after the drinks were consumed. Pardon me, sorry about that. 3 hours later, the blood alcohol content, so we've got 3 hours later, the blood alcohol content decreased to 0.04 grams per 100 milliliters. So now we've got something that's happened after 3 hours. It says, find a linear model that describes the elimination of alcohol from the blood after the peak blood content is reached. According to the model, what is his blood alcohol content 5 hours after it's been released? So the first thing we need to think about is we need to figure out what the slope is. So on this problem, the slope is going to be the change in our blood alcohol level over the change in time. Well, we already talked about the fact that 3 hours have gone by. So the amount of change is 3 hours in time. And the blood alcohol went from, at 3 hours, it was 0.04 minus what it was in the beginning, 0.08, which is going to be negative 0.04. And that's the blood alcohol level, which when you divide these two, you're getting approximately negative 0.0133 blood alcohol level per hour. Okay, so our blood alcohol level, if we want to calculate that, is going to be our initial value, right? If we're going to do, so this is our y equals, they're putting the B in front. So the starting point, B is your starting point, and we started out with an initial value of 0.08 blood alcohol level plus M is your slope, and we found where our slope is negative 0.0133 every hour, and we're going to multiply that by the amount of time and hours that passes by. So this would be our equation that we could write. So it says, well, if you wanted to know specifically 5 hours, so if T is equal to 5, you would say, well, the blood alcohol content is going to be 0.08 plus negative 0.0133 times 5. Now, another way to write this would, most people are not going to put plus or minus here. So it would just, plus or minus is just minus doesn't really matter which, they both would get you the same answer, but I just want to point that out to you because it's not really normal to see plus and minus in an equation. So minus 0.0133 times 5 ends up with a blood alcohol level of 0.0135. Okay, and they told us that that was in grams per 100 milliliters in the problem. Okay, so keeps going down. After 5 hours, you're still getting less. Okay, write an equation for the price and demand of pineapples. Then determine the price that should result in the demand of 75 pineapples per day. So we already came up with this equation, right? We've got y equals mx plus b. So y would be our demand. M is our slope. And we calculated our slope, and on a previous problem, we said we're losing -10 pineapples every time the price goes up $1. X would be the number of pineapples, and B is our starting point. Well, on this problem, on the x-axis, we're starting out with 100 pineapples. Okay, so the question says, determine the price that should result in a demand of 75 pineapples a day. Okay, well, the demand is our y. So we would plug in 75 for y, and we would solve this problem. So we would try to get x by itself. We would need to subtract 100. 75 take away 100 would be -25. And equals -10x. Then we would want to divide by -10. And so x is equal to -25 divided by -10, which is 2.5. And what does x represent here? X is the price of pineapples in dollars. So at $2.50, we would expect to sell 75 pineapples per day. So creating a linear function from 2 data points. Let's just work through one of these problems here. Here's an explanation of how you do that. But this says, in 1912, the world record in the men's 100-meter run was 10.6 seconds. The world record dropped to more than a full second below that in 2009 when Usain Bolt ran 100 meters in 9.58 seconds. Okay, and if you look on here, that's your y value. Okay, so we're going from 10.6 to 9.58, which is the 2 points that we've got here. So we're actually we're not rising, we're falling, right? So when we do rise over run, okay, we're going down. So we would say, sorry about that. So we would actually take the 9.58 minus the 10.6 to get how many seconds we fell. Okay, then our run part is in years, and we're going from 0 to 100, and so 100 minus 0. Now, one thing you'll notice is that this point right here is 9.58. Sorry, it's 100, 9.58. Both of these go with that. This point right here is the point 0, 10.6. And both of these go with that. So 9.58 minus 10.6 is -1.02. 100 minus 0 is 100. When we divide these, we're getting 0.0102, and this top is represented in seconds per, the bottom is years. Okay, so there's our slope. So if we want to write the equation, y equals our slope, which would be negative 0.0102, times the time that goes by, plus our starting point. Well, what is our starting point? We're going to have to look at our y-axis here and go, okay, well, we started right here at 10.6. So it says substitute the values for the data points 0, 10.6 to find b. We already did that. It's 10.6. And use the value of m and b to write your general equation. And y equals negative 0.0102 t plus 10.6. If we actually substituted in what they're saying, sorry. So there's our equation of our line. Until 1850, humans used so little crude oil that we can call the amount zero, at least in comparison to the amount used since that time. By 1960, so in 1850, we're basically using zero amount of crude oil. By 1960, humans had used a total cumulative of 600 billion cubic meters of oil. Create a linear model that describes world oil use since 1850 and discuss the validity of the model. Well, we have a data point at 0 time has gone by, 0 oil. And this represents time that's gone by since the year 1850. We have another point that would be our, so another way to represent this would be 1850, 0. From 1850 to 1960, there are 110 years that have gone by, and we've used 600 billion, and I'm going to put that in my problem, that this represents billions, cubic meters of oil, or we could write that 1960, 600. Okay, so if we want to find the slope, we would have to subtract our y values. So 600 minus 0, and we would have to subtract our x values, 960 minus 1850. Well, that's going to get me 600 billion over 110. So 600 divided by 110 is, I'm going to round this to approximately 5.45. So this is an approximation. And this would be billions of cubic meters of oil per year. Okay, per year. So it says, look for an equation of the form y equals mt plus b. Well, we found m is approximately 5.45 billions of cubic meters of oil per year. B is our starting point. So at the starting point, they said that we basically didn't use any in 1850. So our equation would be y equals 5.45 billions of cubic meters of oil every year plus 0, because our starting point here is, it said we kind of came out with nothing. So it says draw the graph only for the years after 1850. So we don't really know what happened at 1850, but we do know our starting point is 0. So if I plug in 1900, well, how many years have gone by from 1900 to since 1850. I'm just going to find some data points. So I know that the year 1900, so we know that 0 represents 1850, and at 1850 we had about 0 use of oil. Okay, in 1900, that's after about 50 years has gone by. So if we plug 50 into our equation, we would have y equals 5.45 times 50 plus 0, which we don't really need the plus 0, but that's just saying that we weren't really using any to begin with, but now we are. I'm getting 272.5, and that would be billions of cubic meters of oil per year. So 272.5, somewhere around right in here. I know it's less than 300. That might be a little bit too high. Okay, so 300, about halfway in between those. So we know it's a little bit less than 300. Okay, into the year 2000, there would be 150 years have gone by. So we would plug in 150 there. Okay, so if we plug in 150, 5.45 times 150 plus 0, that's going to be 817.5 billions of cubic meters. So 800 is right here. So maybe just a little bit higher than 800. So on this graph, when we're plotting the points, it's going to kind of look like this. Basically, it's skyrocketing, right? If you look at what's going on with that oil. On Friday, we'll have a real brief lesson on the support for 9B. There are 5 questions there. So I will post that video on Friday as soon as I get done recording it. But other than that, we are done with 9B.